Okay, so 2.9 is our second to last section in Chapter 2. We have two more derivative rules to learn. And they're not really rules so much as derivative of specific types of functions. We've got exponentials and logarithms. And so today we're going to look at exponentials. So here it says, example 1, sketch the graph of e to the x, and then on the same set of axes, sketch a possible graph of f prime. All right, so e to the x is one of your parent functions. Pre-cal is just getting acquainted with e to the x these days. The graph, remember, has a horizontal asymptote on the x-axis, but it's only affecting the graph on the left end. It comes from the 0, and it increases very rapidly once it gets past x equals 0. But it does cross through 0, 1, and here is f of x. Yeah. Okay, cool. Remember, e is about 2.718. So now what we're going to do is, on the same function, we're going to graph the derivatives, and I'll do that in a kind of a seafoam green color. Now, what you want to do when you're sketching the graph of the derivative of a function is, first of all, look for any places where you know the exact value of the slope, which would be 0. So you're looking for local max or local mins. Do we have any local max or local mins? No. So what we do notice about this is, since this function is monotonic increasing, its derivatives should all be what type of number? Positive. So I'm going to graph the derivative on the same graph. Much like the function itself, the y values of the derivative are going to be entirely above the x-axis, or positive. So now that we know they're all positive slopes or positive derivatives, let's see how they're positive. So I got my little meter stick here. I will analyze the slope way over here to the left. At that point, the graph is pretty flat, so the tangent line is a pretty small positive number. A pretty small positive number. So at that value of x, where I just had that ruler held at this value right there, I'm going to go ahead and plot a pretty small positive number that represents the slope of the graph there. Maybe right there. As I move to the right from that point there, my graphs are still positive, but they're slowly increasing. So right about there, I have another positive slope that is a little bit bigger than the previous one. So at that value of x, I'm going to put another small positive number that's a little bit bigger than the previous one. On the y-intercept, once again, we have a positive slope, and it's a little bit steeper than the previous one. So I'm going to draw another positive number that's a little bit bigger, maybe right there. And as I go to the right, as my y values get bigger, so do the slopes. So the y values are increasing very rapidly, and so are the slopes. So at a couple of values of x, I'm going to draw a big y value, and then here maybe another y value that's even bigger. And now all I have to do to get the graph of f prime is kind of connect the dots in betwixt where I took my qualitative, not quantitative, measurements. And it looks something like that. All right. So what it appears to be doing as we go out to the left is, as the y values approach 0, the slopes are approaching 0 as well. They'll never reach 0, but they're approaching 0. So it would appear that the graph of the derivative of f prime, or I'm sorry, the graph of the derivative of f, namely f prime, is itself an exponential function. Now I just put arbitrary y values there. My y values end up being directly on top of the y values that I had. That's not necessarily the case. So what we're going to do now is we're going to go to the calculator. Because if the way I drew it is correct, which I doubt it is, then if the function is e to the x, then the derivative should be what? It should be either e to the x or something else of the form b to the x. I do know that the derivative appears to be another exponential function. So if it's not itself, it's going to be something very, very similar to itself. Now the calculator is a number cruncher. It's a quantitative tool that we can use to actually compare values. So you don't have to get your calculator out, but I'm going to go ahead and do what we did back when we learned how to graph the derivative. Remember, using our 84s without actually having the equation. in y1, I'm going to go ahead and type e to the x. That's second ln of x. So let's go ahead and pick a nice window here. Let's go from like -5 to 5. And then our y-min, we'll go from like -0.5 to 10. Let's see if that's a pretty enough window. Ooh, how do y'all like that? There's e to the x. It's blue. I drew mine in red. Now what we're going to do in y2 is we're going to let the calculator graph the derivative. So remember how to do that? In y2, we type math number what? 8, right? And I'm in math print, so we're going to take the derivative with respect to x of what's in y1. So you can either type in e to the x again or hit alpha trace number 1. And now here's how we're going to let it compute it and graph it for all x. You put an x there. Now it might take a little bit longer because it's computing a bunch of slopes and connecting the dots. So very similar to mine, the calculator appears to have drawn it on top of the original function. But remember, that is only a graph, and looks can be deceiving. It could be that the y values are so close to each other, it can't create another graph. So how can we then convince ourselves that it is the same graph? You could zoom in or go to the table of values. Yeah, if you hit table, which is table is under the graph, so second graph, it should be set up by default to automatically generate. So now if you compare for these values of x, compare the y values. If you scroll into the column, it'll put the number with more decimals down below. So there's y1, that's the y value at 1, and there is the slope value at 1, 2.718, 2822, 2818. Oh, 2818 and 2822, those aren't quite the same. But they appear to be the same to at least what? 5, right? 5 decimal places. And then if you scroll down, it looks like they are pretty much the same except as you go deep into the decimals. So remember, your calculator is not going to really store or have all the values of the derivative completely 100% correct because it's doing it numerically. But there is enough evidence here to show, at least if you just looked at the columns, that they are in fact the same y values. So there is more evidence to the claim that the derivative of e to the x is what? E to the x. And guess what? It actually is. Okay? So here is it formally stated. The derivative of e to the x. That's what this box is called. And it says the derivative of e to the x is e to the x. It is its own derivative. That's pretty cool, right? It is its own derivative. Now, what I'm going to do for you is play a song. Play a song. And I got to see how I can do this with my microphone turned off. All right, here we go. Hang on.